We're all a bit obsessed with averages, the average commute, the average score, the average price. But what if the average is actually hiding the most important part of the story? Today, we're diving into variance, a way to measure consistency that honestly is often way more important than the average. I mean, really think about it. Would you rather have a bus that's on average, on time, but one day it's 20 minutes early and the next it's 20 minutes late? Or would you take the bus that is always, consistently, just 2 minutes late? When it comes to planning your life, consistency is absolutely king, and today we're going to learn exactly how to measure that. And look, this isn't just about convenience. It can literally be a matter of life and death. The U.S. General Accounting Office, for instance, keeps a close eye on water treatment plants. Now, for them, the average level of a pollutant is important, sure, but the variance, that's critical. A sudden, unexpected spike in pollutants could be dangerous, even if the average stays low. Low variance means the system is stable, it's predictable, it's safe. So, here's our game plan. First, we'll talk about why we're even on this quest for consistency. Then, we'll get into the tools for gauging the spread of a single group. After that, we'll level up and learn how to compare two different groups. And finally, we'll bring it all home and talk about why this stuff really, really matters. All right, first up, the quest for consistency. In the world of manufacturing or finance or even getting packages delivered, predictability is profit, reliability is safety. We've got to have a way to look past those simple averages and get a real solid measure of how reliable a process is. And that measure is called population variance. It's represented by that little Greek letter sigma squared. Just think of it like this. Low variance means all your data points are huddled together nice and tight, like a pro archer hitting the bullseye over and over again. High variance? Well, that means the data is all over the place, like an amateur's arrows landing all over the target. And let's be real, we all want to be the pro archer. Okay, so we know what we want, low variance. But how do we know if we have it? How do we actually test if a process is consistent enough? Well, for that, statisticians have a very specific, very cool tool. It's called the chi-square test. Now, the engine behind this test is something called the chi-square distribution. It looks like that Greek letter chi squared. And yeah, the name might sound a little intimidating, but don't let it fool you. Just think of it as a specialized ruler that we use for one thing and one thing only, measuring variance. And as you can see here, it's not just one ruler. It's more like a whole toolkit. The shape of the chi-square curve actually changes based on something called degrees of freedom, which is basically just a fancy way of talking about your sample size. To put it simply, the more data you collect, the more precise your measurement is going to be. So, let's make this real. We've got St. Louis Metro. They want to project this image of being super reliable. They have a company standard for their best arrival times, and we're going to use our new tool, the chi-square test, to see if they're actually living up to their own hype. And to do that, we're going to follow a really straightforward 5-step recipe. First, we state our assumptions. Second, we pick our tool. Third, we run the numbers. Fourth, we find our line in the sand. And fifth, we make the call. It's as simple as that. Step 1, the hypotheses. Okay, so the company policy says the variance in arrival times should be 4 minutes or less. So our starting assumption, the null hypothesis, or H0, is that they're meeting that standard. The alternative hypothesis, or HA, is what we're trying to prove, that the variance is actually greater than 4, that their service is just too unpredictable. On to steps 2 and 3. Our tool is the chi-square test, and we use this formula. Now, I know it looks a little complicated, but all it's really doing is taking our sample size, in this case 24 bus arrivals, the variance we found in our sample, and the company's claim of 4, and it cooks them all down into a single score. We plug in the numbers from our study, and out pops our score, 28.18. So, now what? We have a number. What does it actually mean? Is 28.18 big enough? Is it extreme enough to prove that the bus service is unreliable? And that, my friends, brings us to the final steps, making the decision. This graph shows our line in the sand. That shaded area on the right, that's the rejection region. If our number, 28.18, had landed in there, we could have shouted, aha, the variance is way too high. But it didn't. It falls just short. It's just not extreme enough to throw out our initial assumption. So what's our conclusion? In plain English, it's this. Based on our sample, we just don't have enough evidence to say the bus service is excessively inconsistent. For now, it looks like they're meeting their goal. Okay,
But what if you're not just checking one company against some rule? What if you actually have to choose between two different options? Well, welcome to our next section, a tale of two variances.
So let's do a quick recap. To check the consistency of one group against a standard, we use the chi-square test. Easy enough. But what if we need to compare two groups to see which one is more consistent? For that job, we need a new tool. Say hello to the F-test. And let's set the scene. Imagine you're an administrator for Dallas County Schools. You need to hire a bus service. You've got two companies in the running, Millbank and Gulf Park. Price is one thing, sure, but you know what really matters? Consistent, reliable arrival times for the students and peace of mind for the parents. So, which company do you choose?
And this is where the F-test is so brilliant. It's actually super simple. All we do is calculate the variance for each company from our samples, and then we just divide one by the other. That gives us a ratio. See, if their consistency was perfectly identical, the ratio would be exactly 1. The more different they are, the further away from 1 our F statistic is going to get. So in this case, after we run the numbers on their arrival times, our F statistic comes out to 2.40. What that's telling us is that the sample variance of one company is 2.4 times bigger than the other. But the big question is that difference statistically real, or could it just be a random fluke in our data? And the verdict is in. After we check our F statistic, we find that a difference this big is really unlikely to be just random chance. And that means the school administrators have solid evidence to say, yes, there is a real difference in reliability between these two companies. So we've gone through the numbers and the tests. Let's zoom out now for our last section and talk about why any of this actually matters. Because this isn't just for homework problems or bus schedules. Understanding variance, it's like having a secret superpower. Here's the ultimate cheat sheet. If you want to know if your own process is stable, whether that's a production line at work or just your morning commute, you use a chi-square test. But if you have to choose between two options, two suppliers, two investments, two different brands of coffee, and you want to know which one is more reliable, you use an F-test. So I'll leave you with this. Now that you have these tools, now that you can look beyond the simple average and actually measure consistency, where are you going to see the world differently? Are you going to think about the variance in a factory's products? The volatility, which is just variance, of a stock? Or will you maybe just find yourself wondering about the statistical consistency of your favorite barista? The applications are absolutely everywhere. Thanks for tuning in.